Hello everyone, in this video we are going to talk about the different methods of solutions of first order first degree differential equations. So let's talk about the general form of first order differential equation. It takes this form dy by dx equal to f of x and y. So the right hand side can be any function of x and y. This form can be conveniently written in this one, m of x and y multiplied by dx plus another function n of x and y multiplied by dy equal to 0. And we can always transform this form dy by dx equal to f of x and y to the other form around, m of x and y dx plus n of x and y dy equal to 0. So let's take an example to clarify this point. Assume that we have differential equation dy by dx equal to x minus 2y over y minus 3x. In this case, if we want to put this equation in the required form, what we need to do simply is to multiply both sides together, and we put everything in the left hand side. Then by comparison we can identify our functions m and n, and if we do this for this function, we will have x minus 2y dx plus 3x minus y dy equal to 0. So by comparison here, if we compare the two terms that are multiplied by dx, we can find our function m, and if we compare the two terms which are multiplied by dy, we can find our function n of x and y. And this is how we can put the differential equation in this form. Okay, now let's talk about the solution of differential equation. As we know that the differential of differential equation contains a number of arbitrary constants equal to the order of the differential equation. And since we are dealing now with first order differential equation, so we expect the general solution to have only one arbitrary constant. So let's assume that this is the form of the general solution that we expect from this differential equation. And so here we have this constant c is arbitrary constant, and this one here we usually determine using the initial conditions associated with the differential equation that we are solving. If we differentiate this equation, we will have du equal to partial u by partial x dx plus partial u by partial y dy, and this will equal to 0. So here, since we assume that this function u of x and y equal to c is the solution to the given differential equation, then it has to be true that the differential equations that we have obtained is exactly the same as the given differential equation. And so by comparison we can conclude that partial u by partial x is equal to the function m of x and y, and partial u by partial y is equal to the function n of x and y. And this has to be true, otherwise we can't claim that the function u of x and y equal to c is the solution of the given differential equation. And we will use this simple conclusion to find our solution later, as we will see. Okay, so now we have differential equation in this form, m of x and y dx multiplied by dx plus n of x and y multiplied by dy equal to 0, and we expect the solution takes this form u of x and y equal to constant. So our question here now is how to find this solution function. In order to answer this, we will consider three different cases. The first case here, if the given differential equation is exact. And by exact, we mean that this differential equation has the property of exactness, and we will learn after that how to check this property and the meaning of this one. And if our differential equation is exact, then we can find the solution by direct integration, as we will see. Now the other case, if the differential equation is not exact, but we can put it in exact form by using any of these three techniques. The first one is the technique of separation of variables. So if we are given differential equation that is not exact, we can put it in this exact form if we can make separation of variables. And the other technique that we can try is by looking for some integrating factor, which is some function to multiply in this equation to make it exact, And the other, or the third case, is if we can put the differential equation in the form of Bernoulli equation or linear first order differential equation. So any of these three cases can convert to the differential equation from non-exact to exact. And the last option that we have here, if the first two methods are not satisfied, is to try these two techniques. The first one is the change of variables. So we think of some transformation of variables to facilitate and make the solution of the differential equation easier for us. And otherwise, if all of the previous methods are not working, then we look for the method of inspection. And in this method, we look for integrating factor, some function, which now depends on both x and y, which can convert the differential equation into exact differential equation. We will talk about each of these methods in details, and we will give examples to clarify the points. For the next video, we will consider the first case of exact differential equation. Thank you.